Hi everyone, I'm Connor, and today I'll be talking to you about Lab 7, the transformer. In this lab, you'll be asked to use a transformer to translate from Spanish sentences to English sentences. In particular, you'll be asked to implement the attention mechanism of the transformer. As we've seen in class and in the readings, a transformer is an architecture that allows us to translate from one input sequence to an output sequence of a different domain. In this case, it's French to English translation. The transformer consists of two different networks. First, the encoder takes in the input, in this case a tensor representation of the input words, and outputs a context tensor. This context tensor represents the meaning of the sentence. This context is then given to the decoder, which takes this context tensor and turns it into a tensor representing English text. This is a closer look at the encoder and decoder layers. Most important is the self-attention and the encoder-decoder attention, which we will be implementing as multi-headed attention modules. As you know, attention is a mechanism that allows the network to learn how to focus on different parts of the input, shifting its focus as it goes along the sequence, allowing it to put more weight on important information and allowing it to ignore information that isn't important at the moment. In this diagram down here, we can see a French sentence on the left split into separate tokens, and the English translation of it on the top also split into several tokens. And this represents the attention that the network has decided to put on each of these words in the sequence. As we can see, the attention is mainly placed on the diagonal, which means that for most of the sentence, it's sort of a one-to-one mapping of one French word to one English word. However, we can also see, especially in this section here, that it does differ. Specifically, that English puts its adjectives in a different order than French does, and because of that, this module, the attention module of this network, needed to learn how to shift its attention around according to the input sentence. This is the scale dot product attention function that you'll be implementing in your lab. It takes in three inputs: a query tensor, a key tensor, and a value tensor, and outputs a tensor of the same size. All these tensors are the exact same size. They all consist of a batch dimension, and within each batch dimension you have a matrix consisting of a token dimension, which we can think of as the word dimension, and an embedding dimension, which is size D model. So what we do first is we multiply the key and query matrices together, and this determines how close the query and the key are to each other. We then scale the output, perform a masking operation, which you already have the code to do that, and perform a softmax on it. And what that gets us is a percentage of how close the query and key are to each other. Then we multiply that with the value matrix, which will weight the values higher where the query and key tokens match. And then that will provide a single attention tensor. This is a diagram of the multi-head attention module that you'll be implementing in your lab using the scale dot product attention function. Just like in the dot product attention function, you'll have three separate inputs, one for value, one for key, and one for query. However, unlike the scale dot product attention, these will all be three separate copies of the same input tensor. However, our network will learn how to turn them into value, key, and query tensors using three separate linear layers per head. We then pass the outputs through the scale dot product attention function, and that will give us a single attention tensor. We will perform this operation h separate times, one for each attention head, to allow our network to focus on multiple different things at one time. And so we'll need to have h different pairs or h different triplets of linear layers. So a total of 3h linear layers. And note that these linear layers, while they'll all look the same, they need to have separate weights and will not simply be copies of each other, so that they can learn how to focus on different things using the scale dot product attention. Once we have the outputs of all of our attention heads, we will concatenate them together to combine them into one single tensor, and then we'll use one linear layer to turn it into one single attention header, one single attention tensor that will be used in the transformer modules. The only things that you're asked to implement in this lab are the attention function, which is the scale dot product attention, and the multi-headed attention module. Everything else, including the transformer, the data set, and the training and testing loops, are already implemented for you, and will create a multi-headed attention module which will use your attention function. So you should be able to implement these and then run everything fine, and it should give you a good translation. And the reason why this lab is a bit shorter, and the labs going forward are going to be a bit shorter, is not only so that we can focus on these more intense and involved ideas, but also so that you'll have more time to work on your final project, which you should be getting started on pretty soon. And I also wanted to talk a little bit about the data set that we're using in this lab. So the data set is text from General Conference. It has Spanish text and the corresponding English text. And then your transformer will be creating a translation prediction. Now, one thing to note is you may not necessarily get exact translations. The reason why we're going from Spanish to English is so that for those who don't speak Spanish, you can pretty easily look at these two sentences and see how close they are if they don't match directly. For example, he heard my voice is pretty similar to he listened to my voice, so that's definitely a good translation. Another thing to keep in mind is that census was taken from General Conference and not created specifically as a translation data set. The data set's very noisy, so there are things that are translated differently in the two languages, and there are also things that sentences that may be misaligned in the data set. So you shouldn't expect your results to be perfect, but you should expect that in most cases you can get a decent translation. And I just wanted to show you this just so that you have an idea of sort of what to expect. Another interesting thing is this unknown token, which means that whatever text was there originally in the dataset document couldn't be translated into an embedding. So whatever embedding function we use just doesn't have an embedding for that word. Maybe the word's misspelled, or maybe it's just some word that for whatever reason it just doesn't have a good embedding for. And so there are a lot of cases where your translation may not be perfect, but it should be pretty decent. And so if you have any questions as you're doing this lab, be sure to reach out to us, to the TAs, either through our office hours or through Slack. And good luck.